Section 10.3 Polar Coordinates. The polar coordinate system consists of a point called the pole, or origin O, a ray starting at the pole called the polar axis, and other points P represented by r theta. R is the distance from O to P, and theta is the angle, usually measured in radians, between the polar axis and the line OP as in the figure. R and theta are called polar coordinates of P. So recall that the Cartesian or rectangular coordinates that we're used to can be drawn in a sort of grid, where we get a whole bunch of distances for our y-axis and a whole bunch for our x-axis. So we basically get tons of rectangles when we grid everything together. So for example, the point 2, 1 would be right 2 and up 1. But in polar, the point 2, 1 looks a lot different, because we don't go along a rectangular grid, we go along a circular grid. So what we do is we look at a whole bunch of circles, one after the other, and we go to the circle that corresponds with our first coordinate for r, and then we move along the circle at a certain angle corresponding to our second coordinate, theta. So the point 2, 1 would be on the second circle, or the circle located at radius 2, and we would go 1 radian. So be something like maybe over here. So that would be the point 2, 1. So notice the point 2, 1 in polar does not correspond to the point 2, 1 in rectangular. If we wanted to convert this point and move it over here somehow, it would look a little bit different. So in polar, just a refresher, we count how many circles we're going to go outward for our value. So in this case, r was 2, just my example. And then we move along at a certain angle that corresponds to our theta value. So in this case, theta was 1 radian. So I moved along 1. So let's do, I think, a more concrete example, where we take a look at a specific point and plot it without all this mess. So how about 0.15 pi over 4? So we draw our polar axis, and we have our origin, and then we move along until we get to 5 pi over 4. Once we move along 5 pi over 4, we just keep moving along over here a distance of 1. So maybe I make it a little bit shorter, but it really doesn't matter. You can call 1 wherever you want. So how about we say that's 1, and this will be the point 1, 5 pi over 4. Because this angle over here is an angle of 5 pi over 4. How about if we have 2, 3 pi? So I should draw my polar axis, and here's the origin. And then I will rotate around 3 pi. So here's 1 pi, 2 pi, and then 3 pi. So it goes all the way around. And then I have to go outward 2. So let's say that here's 1, and then over here is 2. So this is the point 2, 3 pi. Remember, this angle is angle rotated all the way around 3 pi. So if we have 2 minus 2 pi over 3, then we draw our polar axis, we put our origin over there, and we rotate around in the negative direction. And we'll go around minus 2 pi over 3. And then we go down 2 for our radius. So how about we say that this is 1, and then over here is 2. So this is the point 2 minus 2 pi over 3. Lastly, what if we take a look at the point minus 3 pi over 4? So we'll start with our polar axis, maybe a little bit higher, and we will rotate out 3 pi over 4. So it's something like that. But then we take a look at our radius and it's minus 3. So we can't keep going up here to 3. Instead, we have to go backwards. So we go backwards until we get to minus 3. So how about we put that, I don't know, over there. So this would be minus 1, and this is minus 2, and then this is minus 3. So this is the point minus 3 pi over 4. And the origin's over there. The interesting thing about polar, you might have noticed, is that this is not the only possible way of expressing this point. What I could have done was I could have started at my polar axis, and I could have gotten over here to this point instead of by rotating around in the counterclockwise fashion, by rotating in the clockwise fashion. So I could have rotated by minus 3 pi over 4, and I would still get to this same point over here. You know, like that. So this point would be 1 minus 3 pi over 4, but it's indistinguishable from the point 1, 5 pi over 4. It doesn't matter whether I go backwards or forwards. Similarly, I could have gotten to that point using an even longer method. If I decided I wanted to rotate around a whole bunch, I could have went around, and then it went around again. So I would end up going around, let's say, 13 pi over 4. You could just go around as many times as you want, as long as you end up in the same exact place as you were before. So in this case, we have the point 1, 13 pi over 4, which is the same as the point 1 minus 3 pi over 4, which is the same as the point 1, 5 pi over 4. In fact, you could even get by without having to think about the positive radius. If you really want, let's say you had a negative radius, you wanted to make it positive, or a positive, you want to make it negative, well, you could get around the other direction, because I could rotate to pi over 4 and then flip and get over here. All I have to do is take the 1 and make it negative, and that allows me to go backwards. So there's lots of different ways you can get to the same exact point in polar coordinates. All 4 of these represent the point 1, 5 pi over 4. So unlike in Cartesian coordinates, where we had, let's say, the point 2, 1, there was only one specific way of thinking about the point 2, 1. In polar, we have to be a lot more careful. So this means that converting back and forth between polar and Cartesian coordinates can be a little bit messy. If we're going from Cartesian to polar, then we have to consider which choice of polar we're going to go with. But if we're going from polar to Cartesian, then we don't really have to worry so much, because there's not a whole lot of options in Cartesian coordinates. Remember that x and y are r cosine theta and r sine theta for a circle of radius r. We also have, by the Pythagorean theorem, that r squared is x squared plus y squared. And then the tangent of theta is just y divided by x. If you draw a triangle inside of the circle, it's the opposite over adjacent. So using all of those properties of circles, we can convert back and forth from polar to Cartesian coordinates. So for example, if we have the point 2 pi over 3, then r is equal to 2, theta is equal to pi over 3, so we get that x is equal to r cosine theta, which is 2 times the cosine of pi over 3, which is just 2 times a half, which is 1. So y is equal to r sine theta, and that's 2 times the sine of pi over 3, which is 2 times rad 3 over 2, which is just rad 3. So this is the point 1 rad 3. Point 2 pi over 3 becomes 1 rad 3 in Cartesian. If we want to represent the point with Cartesian coordinates 1 minus 1, then that's slightly more tricky because we have to make some choices. So how about we choose r to be positive? We saw that we could do it with negative r, but just to make things a little simpler. So r is the square root of x squared plus y squared because r squared equals x squared plus y squared, and r is positive. So that would be the square root of 1 squared plus minus 1 squared, which is the square root of 2. Let's see what our theta is using the fact that tangent theta is y over x. So y over x is just minus 1 over 1, so it's minus 1. So when is tangent equal to minus 1? Well, tangent is negative in the second and fourth quadrants. So we have to be a little bit careful here because we have to make sure that we're consistent with our original point. If we're looking at 1 minus 1, that's not in the second quadrant, that's in the fourth quadrant. So we can only consider tangent values in the fourth quadrant. So that means that theta is either minus pi over 4, if you want to go backwards to get into the fourth quadrant, or if you want to go forwards, theta is equal to 7 pi over 4. By forwards, I mean counterclockwise. By backwards, I mean clockwise. So that means that we have two possibilities for our point. We have square root of 2 and minus pi over 4. And we have square root of 2, 7 pi over 4. But as we said before, these are not the only two possibilities. We could have made square root of 2 negative to go backwards and then changed our angle. And then we would have gone in the second quadrant instead of the fourth. Or we could have added any multiple of 2 pi to our angle. We just go around again. Just like over here, we basically just add another 2 pi to it. So we have tons of possibilities, just to pick one. Let's talk about curves now represented by polar coordinates. So if we want to think about the curve represented by the polar equation r equals 2, that's the curve represented by every single possible point that fits those criteria. In this case, the only criteria is that the radius is 2. There's no restriction on theta whatsoever. So our angle could be anything. So what we could do is draw our polar axis. Over here is, let's say, r equals 1. So then over here would be r equals 2. But it's every possible point at a distance of r radius, no matter what the angle is. So I could go up over here at an angle, I could go up over here, I could go up over here, I could go up over here. I could go to any of these points that are all a distance of 2. And all of them are part of this, all satisfy this equation. So there's infinite numbers, so I can just connect all of them. And theta can be anything, so don't have to worry about theta. So here's our origin, and here is our curve r equals 2. So it's a circle with radius 2. So we've seen what happens if r is constant. Let's see what happens if theta is constant. Well, then this is every single possible point that satisfies the equation theta equals 1. So if we draw our polar axis, then we're looking at all of the points at a fixed angle of 1. So we move our angle 1 radian, and we consider the point over here, let's say r equals 1, but r could be anything, there's no restriction in r, so r could be 2, r could be 3, and so on. So the point 1, 1 is on our curve, the point 2, 1 is on our curve, the point 3, 1 is on our curve, the point 0, 0 is on our curve, the point minus 1, 1 is on our curve, the point minus 2, 1 is on our curve, and so on. So let's see if I can connect these into a straight line. And the answer is no, I couldn't connect them into a straight line, but you can imagine that this line was actually straight. So r equals constant curves are circles, and theta equals constant curves in polar are lines. It's the line theta equals 1. how about we sketch a curve where r is not constant, it actually depends on theta. So in this case, r is our dependent variable, theta is our independent variable. We have theta values and r values. So how about we make a table just like we did with x and y. So if theta is 0, r is 2 times cosine of 0, 2 times 1 is 2. So let's see if we can plot that. So at theta equals 0, we should be at a value of 2. So here it is, 2, comma 0, because we put r first. Then at, how about we do theta equals pi over 6. So then r becomes 2 times cosine of pi over 6, which is rad 3. So we should go somewhere around, like, let's say over here. We rotate at an angle of pi over 6, and we go outwards at a value of about rad 3. So then we just keep doing more points. How about pi over 4? So then we plug that in, we get rad 2. So that's like roughly over here. So that's rad 2 at pi over 4. Right, it just rotates at an angle of pi over 4. We can keep going. But we go to pi over 3 for theta. We get 1. So we get a nice radius of 1. Let's say it's like that. Roughly. Put over there maybe. And this is the point 1 pi over 3. So maybe you could sort of see how this is going at this point. You might see what shape this is going to be. Pi over 2, 0 ends up with us right over here. And 2 pi over 3 we can go next. So that'll be at -1. So it's like somewhere like that, where it's a reflection of the point above it. Similarly, if we go to 3 pi over 4, that'll be minus rad 2. So that'll be a reflection of the other one. So this was at -1, 2 pi over 3, and this one is at minus rad 2, 3 pi over 4. And we can go to 5 pi over 6. See that that's minus rad 3. So somewhere over there. And then if we put in pi, we get -2. So that's the same thing as rotating around all the way over here and moving back over here. So we end up right back where we started. So I think we've come full circle, literally. And maybe your circle look a little better than mine, but that's roughly what you get. So that's the curve r equals 2 cosine theta. It's just a circle. Let's see if we can find a Cartesian equation for this curve. So in order to convert, remember, x is r cosine theta. So solving for cosine theta, we get that cosine is x over r. So now we can replace cosine in our equation, r equals 2 cosine theta, with x over r. So we get that r is equal to 2 times cosine theta, which is going to be equal to 2x over r. So that means that we could solve for 2x by multiplying both sides by r. We get 2x is r squared. So remember, r squared is also x squared plus y squared. That's how we convert. So that means that 2x is x squared plus y squared. So we have an equation now. We have x squared plus y squared minus 2x equals 0. And that's our Cartesian equation for the curve. If we want, we can add 1 to both sides and complete the square to get x minus 1 squared plus y squared equals 1. And then it makes a lot of sense why this is the equation for the circle, because it's just a circle of radius 1 that's been moved over 1. So maybe we should see if it makes sense why the equation in polar would be r equals 2 cosine theta. Well, if we take a look at another look at our circle, what we could do is put it in the xy plane and try to draw on it and fail, but it's okay. How about we put a triangle in our circle? So we can draw a radius at some arbitrary point P. So this is the radius r. It intersects at angle theta. Then we can complete our triangle by drawing that. So let's label this point Q. So we just drew PQ. Let's see what angle P makes. Well, this angle over here corresponds to this part of the circle here, which is 180 degrees, so it must be half as much, so it must be a right angle at 90. And then this length over here is the diameter of the circle. The circle's radius 1, so the diameter is 2. So then if we look at theta, it looks like cosine theta is adjacent over hypotenuse, that's 2 over r. Solving for r, we get r equals 2 cosine theta. So it makes sense that r equals 2 cosine theta is the equation of the circle x minus 1 squared plus y squared equals 1. Let's try sketching the curve r equals 1 plus sine theta. In order to do this, it might be helpful to first draw the sine function the classic way we're used to. We could pretend that theta is the x-axis and r is the y-axis. So then remember the sine looks something like this. So we just have to move it up 1. So we'll put 1 over here, 2 over here, and we'll just move up. And we get roughly that curve. So then here's 0. It has a maximum at pi over 2. It goes in the middle over there at pi. And then a minimum at 3 pi over 2. And then it completes the cycle at 2 pi. So if we want to draw this in polar, it'll look a lot different. What we can do is we can start at theta equals 0. So theta equals 0, we can see that we're starting at 1. So we'll start over here at 1. Then it looks like we should go up. Our radius gets bigger as our angle moves closer and closer to pi over 2. So we should go outward as our radius gets bigger as we get closer and closer to pi over 2. So then over here is theta equals pi over 2. And then by this point, our radius has stretched so much that our radius is at 2, so over here is radius of 1. So we're over here now, we've gone from here to here. Now, how about we go to pi? Notice our radius starts decreasing as we get to pi. And it decreases in the symmetrical fashion to the way that it increased. So we should really just draw the same thing as it decreases back to 1 on the other side. And hopefully yours looks a little bit better than mine. Wow, I really cannot draw this. Alright, I guess that's a little better because my side on the right was a little bit engorged anyway. This is supposed to be symmetrical though. Okay, so this is at theta equals pi. Now we've gone from here to here. So now it looks like our radius continues to get smaller as the radius goes to 0. So we're continuing to travel from pi to 3 pi over 2, But as we do, we should be getting closer and closer to 0. So we do that. Notice that if you draw the radius coming out, the radius is getting smaller and smaller and smaller as you get closer and closer to 0. So this, how about I erase the bottom so that I can fit this in. So I put this back, and I'll just stick in a theta equals 3 pi over 2 over here to show you that that's what angle we're at. So we should just keep going to the end. Notice that after 0 it rebounds and starts increasing in a symmetrical fashion, so we get the rest of our curve, which is called a cardioid because it sort of looks like a heart, I guess. I don't know if it actually looks like a heart, but you can use your imagination. So this is theta equals 2 pi. Let's try another example where r equals cosine of 2 theta. So in this case, we will draw cosine and then use that to help us draw our polar curve. So here is r, we'll put our theta axis, cosine starts at 1, and then it goes down, and then up, and then down, and then up. So it looks something like that. It completes 2 cycles by 2 pi because it's going twice as fast because theta is being multiplied by 2. So I'll put 2 theta over here. And then this is theta. And I can fill in the rest also. Halfway will be pi. And I can put pi over 2 over here. 3 pi over 2 over here. So 7 pi over 4 is over there. And that means over here is 5 pi over 4. And over here is 3 pi over 4. And over here is pi over 4. So let's try drawing this polar curve. So it looks like we should go from 1 down to 0. So we'll start at 1, and then our radius gets smaller and smaller as it goes to 0. And it's 0 pi over 4. Then it goes out again until it gets to pi over 2, where it hits a maximum for the size of the radius. So this is interesting because if I were to draw from here to here, that would be for a positive radius. But this is going backwards. So instead of drawing here to here, I need to reflect it. So what I should be doing is drawing it over here. Let's see if I can do that. Something like that. So notice that I'm basically drawing it over here, but then this point goes and gets reflected to this point. So the entire thing just gets reflected over. So I started with here at 0, and then I traveled until I got to theta equals pi over 4. So this is the line, theta equals pi over 4. And then over here I traveled up until I got to pi over 2. But then when I got to pi over 2, I realized, oh wow, I'm actually got a negative radius, so I flipped it. And here to here is from theta equals pi over 4 to pi over 2. So the radius is back at 1 now, and it's going to start to decrease until it gets 3 pi over 4. So it's going over here until 3 pi over 4, but it's the reflection. So it's flipped, so it's over here. So then over here is it theta equals 3 pi over 4. And then we continue from 3 pi over 4 to pi. So from 3 pi over 4 to pi, it's positive. So that means that I can draw, well, I don't know if I can draw it, but I'll try. So it goes from 0 all the way to 1. And now we're at pi. And we had a maximum 1. So then we continue and decrease until we get back to 0. That's from here to here now, until we're at 5 pi over 4. And then from 5 pi over 4 to 3 pi over 2, we're drawing over here, but it gets flipped. So we get this piece. And then from 3 pi over 2 to here, the radius is still negative, so it continues to get flipped. And then I end up from 7 pi over 4, which is over here, all the way home. And I don't have to worry about flipping because it's positive the rest of it, so oops. So you get something like that. So over here was theta equals pi over 2. Over here is theta equals pi. And over here was theta equals 0 and theta equals 2 pi. And we call this a 4-leaved rows because of the 4 loops. Let's now see if we can do a little bit of calculus with our polar coordinates. So the slope of the tangent line to a polar curve is this mess. So now the question is, why is it that mess? Well, what we can do is we can think of the theta and r as parametric equations for x and y. We can just take theta to pretend that's t. So then r is a function of theta, so everything's in terms of theta, everything's in terms of t. You could think of it that way. So then dy dx, well, from our previous section, we know that the derivative for parametric equations is dy dt over dx dt. So if we take the derivative of y with respect to t, that's the derivative of y with respect to theta. So that's this r becoming dr d theta, keeping sine theta, and then keeping r and taking the derivative cosine, because we have to use the product rule for r sine theta, because r is a function of theta, not a constant. So then we do the exact same thing for our denominator. We take the derivative of x with respect to theta. So we do the product rule. First we take the derivative of this guy, we get that, dr d theta. We take derivative of cosine, and that's sine. We leave cosine in our first term, and we leave r in our second term. You have to be a little bit careful because taking the derivative of cosine is minus sine. So we end up with a minus in our denominator. So let's use this to actually figure out some derivatives. So how about we want the slope of the tangent line? Well, we need dy dx for that. So we're looking at the cardioid 1 plus sine theta that we did in example 7. So we have dy dx equal to dr d theta times sine theta plus r cosine theta over dr d theta times cosine theta minus r sine theta. So in this case, well, derivative of r with respect to theta, that's just cosine, because 1's a constant. So we get cosine theta times sine theta plus r, which we'll write in terms of theta as 1 plus sine theta, and times cosine theta. So everything in terms of theta. Just like when we took dy dx, everything was in terms of t when we did parametric equations. So we finish it up, 1 plus sine theta. Oh, I forgot this is supposed to be a minus. So 1 plus sine theta and sine theta. So we can simplify this a little more. It looks like we can factor out cosine theta on the top. We just get cosine theta times sine theta plus 1 plus sine theta, so that's 1 plus 2 sine theta. And we divide by 1 minus 2 sine squared minus sine, because we have cosine squared minus sine plus sine squared, and we can just factor out So we end up with cosine theta 1 plus 2 sine theta over 1 plus sine theta times 1 minus 2 sine theta. So let's look at our derivative evaluated at pi over 3. So we'll take dy dx evaluated at theta equals pi over 3. So plugging in pi over 3, we get cosine of pi over 3 times 1 plus 2 times the sine of pi over 3 divided by 1 plus sine of pi over 3 times 1 minus 2 times the sine of pi over 3. And we can simplify that to get half 1 plus rad 3 over 1 plus rad 3 over 2 times 1 minus rad 3. Then we can multiply top and bottom by 2, cancel stuff out. We get 1 plus rad 3 over 2 plus rad 3 times 1 minus rad 3, which is just 1 plus rad 3 over minus 1 minus rad 3, which is just minus 1. So that's the slope of the tangent line when theta equals pi over 3. Let's now see where the tangent line is horizontal or vertical. So remember, that's when the derivative is 0 or undefined. So let's take a look at when dy d theta is 0. That'll be when our derivative is 0, because that's in our numerator. So that's when cosine theta times 1 plus 2 sine theta is 0, which is when theta is equal to pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6, because we're only going from 0 to 2 pi. For dx d theta, I want to see when that's 0, so that's looking for 1 plus sine theta times 1 minus 2 sine theta, and that'll be when theta is equal to 3 pi over 2, pi over 6, and 5 pi over 6. So this means that we have horizontal tangents when our dy d theta is 0, so that's at the points where we have pi over 2. If we plug that in to our equation, which was 1 plus sine theta, we get 1 plus the sine of pi over 2, which is 2. So we have horizontal tangent at 2 pi over 2. We have to be careful at 3 pi over 2 though, because notice 3 pi over 2 is in both of these. So that means that we have an indeterminate form at 3 pi over 2. We have 0 over 0. So let's skip that for now and look at 7 pi over 6. So then we have r equals half. So that's another horizontal tangent, because dx d theta is not 0 there. Also at half 11 pi over 6. Let's look for vertical tangents now. Again, 3 pi over 2 is a little bit of a problem, because there's the 3 pi over 2 for dy d theta being 0 also. So we ignore the 0 over 0 for now. We'll have to take the limit for that. But it looks like at pi over 6, there's no other pi over 6 over here, so there will be a vertical tangent at 3 over 2 pi over 6. And there will be a vertical tangent at 3 over 2, 5 pi over 6. So let's look at 3 pi over 2 now. If we take the limit, how about as theta approaches 3 pi over 2 from the left, So we'll do that for dy dx, and we will see if this equals infinity or minus infinity, and then we have a vertical tangent. So remember, we can take limits of products and write them as products of limits. So we're going to take dy dx, which is 1 plus 2 sine theta over 1 minus 2 sine theta times cosine over 1 plus sine theta, and we'll split that into 1 plus 2 sine theta over 1 minus 2 sine theta. And we'll do the other limit separately so that we can multiply them, evaluate it a little bit more easily. So our other limit is cosine theta over 1 plus sine theta. So this one's easy. Just plug in 3 pi over 2, and then you get minus 1/3. The other limit is not as much fun. It depends. If you like L'Hopital's rule, then it's fun. So this is, actually everybody likes L'Hopital's rule. What am I saying? So this is cosine theta over 1 plus sine theta. That's all I got left. And I will take the derivative of the numerator and denominator using L'Hopital's rule because it's indeterminate. So we get minus sine on top when we take the derivative, and we get cosine on the bottom. So as theta approaches 3 pi over 2, sine goes to 1. Well, sine goes to minus 1, but then minus minus goes to 1. And cosine goes to 0, so we get really small in our denominator, so this thing goes up to plus infinity. And similarly, if you look at the limit as theta approaches 3 pi over 2 from the right, you could even tell by symmetry of trig functions that it's going to go to minus infinity. So that means that we have a vertical tangent at 0, 3 pi over 2. So if we were to try drawing this, which of course we should, but hopefully you'd be a little bit better at drawing it than me. Yeah, hopefully you'd be a lot better than drawing it than me. Wow. I was so close until the end. Yeah. So that's our cardioid. As we've seen, we have a tangent over here from part A at 1 plus rad 3 over 2 pi over 3 with slope 1. So that was from part A. But now we also see that we have horizontal tangents at 2 pi over 2, which makes sense. There's a maximum right over there. We also have, let's see, horizontal tangents over here and over here. Right? This is at half 7 pi over 6. And then this one is at half 11 pi over 6. And then we have vertical tangents over here. We've got one at 3 over 2, 5 pi over 6. And then another vertical tangent at 3 over 2, pi over 6. And our last vertical tangent is over here at the origin, 0, 3 pi over 2. Let's try graphing the curve r equals sine 8 theta over 5. So let's see if we can maybe do this with parametric equations. That way we could throw it in our calculator. Some calculators also have polar graphers. In fact, ours does, but pretend it doesn't for now and just see if we can do it with parametric equations. So we have x equals r cosine theta. So in this case, r is sine 8 theta over 5, so this is sine 8 theta over 5 times cosine. And similarly, we have y is equal to r sine theta, so that's going to be sine of 8 theta over 5 times sine of theta. So if we pull out our handy dandy calculator emulator, how about we try going to mode, and we'll try parametric. So then for x, we'll put in, where's sine? There's sine of 8, we'll use t, divided by 5, cosine t, and then sine of 8t over 5 sine t, and we'll hit graph. I'll try zooming in a little bit. It's interesting because it looks like we got a couple loops, and then it started off with like another loop like right over there, but then just cut off. So this implies, I think, that 0 to 2 pi is probably not enough, which is our default. It's probably not enough to trace out this curve. We probably need to go farther. So let's see how many loops 0 to 2 pi we need to trace out our entire curve. Well, let's say that we need n multiples of 2 pi to trace out our whole curve. So we would be looking at sine of 8 times theta plus 2n pi over 5. This would have to be equal to sine of 8 theta over 5, because if it takes 2n pi loops to trace out our entire curve, then it should take 2n pi loops to get right back to where we started. So sine of 8 times theta plus 2n pi over 5 must be equal to sine of 8 theta over 5. However, this is equal to sine of 8 theta over 5 plus 16n pi over 5 just by distributing the 8. So that must be equal to sine of 8 theta over 5. So if this is going to be equal to this, that forces this to be even, or an even multiple of pi. Because otherwise, how could you have sine of something equal to itself? You must have an even multiple of pi being added. So this implies that 16n over 5 is even. And that will first happen when n is equal to 5. So this means that we can plug into our calculator the equations x equals sine of 8t over 5 cosine t, y equals sine of 8t over 5 sine t, where t ranges from 0 to 2 pi. Sorry, 0 to 10 pi, because we're plugging in 5 for n. So let's go back to our calculator now. And we'll go to our window, and we'll change our t max to 10 pi. And we'll graph it. Beautiful. So that looks like it's probably the whole thing. And it's actually 16 loops. Let's now investigate the family of polar curves given by r equals 1 plus c sine theta. How does the shape change as c changes? By the way, these curves are called limicons, after a French word for snail, because of the shape of the curves for certain values of c. I don't know if it'll actually look like snails, because, you know, just with the track record of everything else we've graphed so far, but, you know, we'll keep an open mind. So we'll put our calculator again. This time, let's use our polar mode, because it'd just be easier than having to do parametric. So we do polar, y equals becomes r equals. So we'll put in a whole bunch of values for 1 plus c sine theta. So how about we start with 2.5? So 1 plus 2.5 times the sine of theta. Now pressing xt, whatever becomes theta. So let's go to zoom standard to reset things, and we get this nice looking graph. How about we zoom in a little bit? Move up a little bit so that I don't cut off when I zoom in. Ah, beautiful. So that's our graph at c equals 2.5. So how about let's try another value now. How about 1.7? Looks pretty similar, just the loop got a little smaller. So I'll grab that too. And how about we do 0.7. Keep decreasing c. Ah, the loop disappeared. It's kind of became this smooth little like thing. What if we look at 0.5? It's smoothing out. It looks, like it's becoming an oval. Let's see if it continues to smooth out. Let's look at 0.2. Yeah, it looks really like an oval now. And how about we just do 0. We just get a circle. Makes sense because at 0 we just have r equals 1. Notice it looks a little bit oval on our calculator, but that's because our scales are not even. The x is more spread out than the y. It really is a circle. So let's keep going. Okay, so we just did r equals 0. How about we do some negative values for c now? So we'll do negative 0.2. It got cut off, so how about I zoom out and we'll zoom in on the bottom. Too much, too little. Okay. So there we are at negative 0.2. Let's do negative 0.5. Then it looks like it's the exact same pattern, but it's just in reverse, it seems. Let's see if we can confirm that. Yeah, pretty much looks like it's the same pattern in reverse. Let's go to -1. We get a nice little cusp. I think I skipped the 1 for 1, but I think we can imagine that it would just be this version just flipped upside down. So -2 would just be the same, just flipped upside down. Yep. Okay, so that was pretty interesting. Let's go back and see what we did. We had c equals 2.5 over here. Then we had c equals 1.7 over here. Then we had c equals 0.7. So c equals 0.5. Then we had c equals 0.2. We got a circle at c equals 0. Then we started some negative values. We got c equals negative 0.2. C equals negative 0.5. We did c equals negative 0.8, so we could get a little variety. And we got c equals negative 1. Notice it has a cusp over there where the dimple stops being smooth anymore and starts to become this loop. So that was at c equals negative 2.